All right, so whenever we're verifying identities, we want to try to get one side to match the other side. And we're only going to work on one side at a time. We can't move things from one side to the other. We can work on both sides if we want, or we could do all of our work on one side to get it to match the other side. So for this one here, we have got cosecant of theta over secant of theta, and we are going to try to get it to match cotangent. So one strategy that you're probably going to use a lot is to change everything to sines and cosines. So cosecant, what could I change it to? Oh, hold on, we're back. All right, so cosecant. What is cosecant? 1 over sine. Uh-oh. What's it doing here? 1 over sine of theta. What is secant? 1 over cosine of theta. So now I've got a complex fraction. And pretty much always you do not want to have a complex fraction. So when I have a complex fraction, which is just a fraction inside of a fraction, dividing fractions as easy as pie, we can flip the second and multiply. So this is going to be 1 over sine theta times cosine theta over 1. And to multiply fractions, what do we have to do? Right, just multiply top and top and bottom. So we just get cosine of theta over sine theta. And that is one of our quotient identities. What does cosine theta over sine theta equal? Cotangent of theta, which is what we have on the other side here. So once you have your two sides matching, you are correct. Now, what I'm grading whenever I look at this is I'm looking to see that you show every step and that you do it correctly. Because otherwise, you could just do nonsense and write cotangent theta equals cotangent theta down here at the bottom, and it would be right. So the work is what I'm grading here, not necessarily the final answer, although you do need to get to that final answer. So if you get to these problems and you get stuck, then make sure at the end that you have both sides equal to each other, even if you're just making it up on how to get there, even if you're don't actually know how to do it. It might be that you are closer than you thought, and I'm assuming you understand something for that last step, or it still might be completely wrong, but if you don't get to cotangent theta equals cotangent theta at the end, if both sides aren't equal to each other, that's definitely going to be wrong. And these, of course, will be graded for partial credit, too. Yeah, this will be on paper. Everything we do for this section here will be on paper. Whenever we take the test on Unit 6, there'll probably be an online part and an on-paper part that has a few of these on it, because I can test most of the rest of it pretty easily online, the graphs and whatnot, but in fact, I would rather test it online with the graphs because you can do multiple choice and stuff easier with that. But these I will promise to grade by hand whenever we do, because really I can't ask you these questions unless I have ones that grade by hand. All right, so this one's a little bit more complicated here. So we've got secant squared theta minus tangent theta cotangent theta equals tangent squared theta. So in general, it's probably going to be better if we work with the more complicated side first. So the left-hand side here is a little bit more complicated. We've got a few options on what we can do. So usually, if I don't already have sine and cosine, in a lot of cases, I like to go ahead and change everything to sine and cosine. So secant here would be 1 over cosine squared theta. It is okay here, even though secant is squared, we can still use that reciprocal identity there for the square. And then we'll have sine theta over cosine theta times cosine theta over sine theta. Now, does anybody see anything that is going to happen here? Yes, cosines will cancel and the sines will cancel because we are multiplying those two together. So in order to cancel, you got to have multiplication between the things that you're canceling. And something's got to be on top and bottom. So when all of that cancels, what does it equal? 1. Not 0. It's not gone completely, but it equals 0. So, what we have here is we've got two numbers together. There's a few ways you could go from here. I think what I'll probably do is, if I had common denominators, I might could do something with this. So, right now that's like 1 over 1. So, if I need a common denominator, I would need to multiply by cosine squared theta on top and bottom here. So, I'm going to use a different color for that. You wouldn't necessarily have to show what I'm doing right here. So, I'm going to do that in a different color. If you do, I think it would be all right. So, you got 1 minus cosine squared theta minus cosine squared theta over cosine squared theta, which this is sort of an optional step here. If you wanted to go ahead and tell me that this is 1 minus cosine squared theta over cosine squared theta, that would be okay. All right, questions so far? All right, this looks nothing like tangent squared theta right now, right? So, however, we are actually very, very close. I'm going to actually work on both sides a little bit here. Tangent squared theta would be sine squared theta over cosine squared theta. So notice our denominators right here are already the same. Where's my highlighter? So my denominator right here and my denominator on this side are the same. So what I really need to do is I need to figure out some way to turn this into sine squared theta. So if we look back at those Pythagorean identities, I'm going to do this over here to the side. So this is not part of, this is not part of the problem. I'm doing this over to the side here. We know sine squared theta plus cosine squared theta equals 1, right? So, would it be mathematically possible for me to do subtract cosine squared theta here and subtract cosine squared theta here? So I would have sine squared theta equals 1 minus cosine squared theta. And that is mathematically correct to do, right? I can just move that over to the other side. So this is still equivalent. So what do we see? We see that sine squared theta does equal 1 minus cosine squared theta. Those are the things that I want to change, right? So what we'll say over here is we can just replace that 1 minus cosine squared theta with sine squared theta, and then the denominator will stay the same. And then you could either take both of these back to tangent squared, or you could just say that this equals sine squared theta over cosine squared theta. So you don't necessarily have to get one side to match the other. You could work on both sides, or, you know, it would have been pretty simple here just to call this tangent squared theta and say that it matches over here. So this right here is not a separate identity because it comes from the Pythagorean identity. It is basically just a rearrangement of the Pythagorean identity, but you want to know it because you're going to use it a lot. Yes? No, you cannot move things from side to side. Right, so you can't cancel one side with the other. So all simplification has to be done like working downward on that one side. So we could not like cancel things by sort of multiplying both sides there. Like, just kind of like getting rid of it because it's saying, yeah, we cannot do that on both sides. Yeah. Mm-hmm.
So if you left the secant squared times theta alone, but still left the minus 1, and that equals tangent, would that still work since it pretty much looks like one of the Pythagorean identities?
Okay, great. So, let's see. Well, everybody's got this down, right? It's okay if I erase it. So I like what Zach is saying here, and I like even more that he thought of it, because there's really actually a little bit easier way to do this problem. But it's usually not one that, well, our major problem is usually that students do not have all of the Pythagorean identities memorized. They only have the sine squared plus cosine squared equals 1 memorized, which we're going to memorize them all, but we use sine squared plus cosine squared equals 1 so much that it's sort of what we revert back to a lot. So, so you're saying leave secant alone, right? But do the same thing we just did with tangent and cotangent. So sine theta over cosine theta times cosine theta over sine theta. And so same thing cancels. So we got secant squared theta minus 1. And so Zach was telling me that looks like one of the identities. So the identity is it 1 plus tangent squared theta equals secant squared theta? That's the one that we have, right? Well, we can do the same thing here that we did with our other identity. We can rearrange it. So tangent squared theta equals secant squared theta minus 1. So secant squared theta minus 1 can just be replaced with tangent squared theta. And then so both sides match, and we can do that. So that's even a little bit easier. As long as you recognize that you can do this right here, which is something that sometimes we remember and sometimes we do not. Yes? So, like, the stuff I write down there in the corner, or like this stuff right here that I just write down in the corner, it does not have to be shown as work. So, it is just going to be a fact that that always sine squared theta is going to equal 1 minus cosine squared theta. Because that's just moving that cosine over to the other side. It's the same as our Pythagorean identity. So that is always true. So on that last one where we had 1 minus cosine squared theta over cosine squared theta. This top part right here, because 1 minus cosine squared theta equals sine squared theta, we can just replace 1 minus sine squared theta, 1 minus cosine squared theta with 1 minus sine squared theta over cosine squared theta like that. And so it is also true, you may want to write this down as well, it's also true that cosine squared theta equals 1 minus sine squared theta. So those are not going to be like on a quiz or anything as an identity that you have to know, because they are the Pythagorean identity just rearranged. But these need to be things you think about in your mind when you're doing these problems. Because they come up pretty often. And they're used when you need to change something from a sine to a cosine or a cosine to a sine. Okay, questions? All right, let's try another one. This one looks terrible and super complicated. So, there are also two, in my opinion, equally easy ways to do this. This one's not nearly as bad as it looks. So, a lot of times I say to start with the side that looks more complicated, which would probably be the left side here because you got that fraction. But on the right side, you've got secant and cosecant. Whereas on the left, you've got sine and cosine, which are sort of more simple functions. So there's a couple ways that you can do this. I'm actually going to do this the first. I might do it both ways. That'll work. But I'm going to start with the right-hand side on this one. Because secant is going to be 1 over cosine x. And cosecant is 1 over sine x. And you could go straight to what I'm writing right here. If you want to skip this step, that would be okay. All right, so notice over here for this side, everything is like in one complete fraction, right? Over here we got two separate fractions. So if we got common denominators, I feel like that's going to help us over here, right? So what would the common denominator have to be? Not tangent. What if I had 1/3 and I was trying to add 1/5? What's the common denominator there? It's 15. How'd you get it? You multiplied those together. So over here, these aren't numbers, but it's the same thing. So we would have to have sine x cosine x, which means, I'm going to do this in a different color. I need to multiply this fraction by sine x on top and bottom. And I need to multiply the second fraction by cosine x on top and bottom. And look what this does. That's going to be 7 sine x plus 5 cosine x, which is the other side, 7 sine x plus 5 cosine x over sine x cosine x. So I would be done there. Questions? Alright, does anybody, just to see if anybody out there has got a real knack for this, does anybody see a different way we could do it? At this point, I don't really expect you to. At this point, if you can follow what I'm doing, even though you're thinking, how does she ever come up with that stuff? We're in pretty good shape right now. Eventually, I need you to be able to come up with it on your own. But this stuff at the beginning is certainly not easy to come up with it on your own. Here, I think I've told you guys this before. We've done this before in class, I think, haven't we? We've done the love connection on things. So if we have a fraction with a single denominator, we can divide both things in the top by that denominator. So if I do that here, I got 7 sine x divided by sine x cosine x plus 5 cosine x over sine x cosine x. Over here, what can happen? Sines can cancel, just leaving me with 7 over cosine x right here. Cosines are gone. 5 over sine x. If cosine x is on the bottom, that's like 1 over cosine x. So I could change this to secant x. And when sine x is on the bottom, that's like 1 over sine x. So that'd be 5 cosecant x. Which matches this side over here. And you don't have to know how to do it both ways. You have to come up with one of those ways, right? That'll work. Okay, questions? Alright, so this one you're definitely probably going to need to work on the left-hand side because there's nothing to do to the one on the right-hand side. So we've got sine A over cosecant A plus cosine A over secant A. What do you guys think that we should do here? Okay. We could do that. However, because I know more than you right now, you know that's going to be the long way on this one. So that is a valid thing to try, and it will eventually, I think, get you to the answer. But the reason I'm going to say let's not yet is because the denominators are cosecant and secant, and sometimes it's better to get rid of your functions that are not sine and cosine. So I would change this to sines and cosines first. Now, I say that because I know more than you right now, and I can foresee what's happening here. So cosecant is 1 over sine A. And then cosine of A over 1 over cosine of A. And so you could get common denominators here, but that is going to be even worse, right? So what I'm going to do right here is I'm going to divide these fractions. So sine A times sine A over 1. Just flipping that second and multiplying. And then I've got cosine A and cosine A over 1. So when I do this, I've got to do sine A times sine A. What is sine A times sine A? Sine squared A. And over here, I'm going to get cosine squared A. And what is sine squared A plus cosine squared A? 1, which equals the other side, which is 1. And you eventually could get there with common denominators also. It's just going to add a few steps. Okay, questions?
So just like on these changing the sign cosine
Lots of times. Sometimes it's not the easiest thing to do. Pretty much anytime you like ask a question like that, I cannot give a definitive answer on these because it just depends on. Really, the easiest thing is the thing that you can see and understand. So you might do something that takes more steps, whereas Wesley might do something differently. But what is easiest is different for people here. Sometimes there might be like a way shorter way, but it requires you to remember a more complicated rule that you didn't see to apply. So it's really so much just about what shows up to your mind. There. It's kind of like if you were doing like a problem solving, like a word puzzle, like a puzzle or something. You would probably go about it differently than other people. All right, so we're not going to do that from the book. That's not what we're going to do. Let me pass out. Okay. Okay. So this worksheet here, let's do well, how many am I gonna do here? Let's do 1 through 8. And of course, don't try to put your work on this page. This is not big enough for put your page work on this page. So I'm just going to let you try it and see where you get.